Hello everyone. Today's lesson is going to cover this is going to be the second lesson on the optimization of dynamic systems. And today, if I could spell optimization correctly, so usually in courses that cover this kind of optimal control theory stuff, there'll be more steps where we built from the problem that we started with last week to the problem we currently have, what we're going to do now. But so as a refresher, last week we covered optimizing systems with fixed initial time and fixed terminal time, and just specified states at either the beginning or the end, and not kind of mixed state constraints or more complex state constraints at the beginning and the end. In a normal course, you would then add free final time, and then adding mixed state constraints at the beginning and the end, and you could add then free initial time. I'm just going to go straight to the problem that is kind of what Beluga uses, because the techniques are the same, it's just less repetitive. If we skip to general, initial, and terminal constraints with free initial and final time. And a lot of times you don't see initial time being free, but it matches final time, and I kind of really prefer it because then you get the most general problem that is solvable on a single arc, and it's what matches what Beluga does. So we have some cost functional J, which we minimize with respect to U, and we have an initial cost now, phi naught, and that's based on initial time T naught and the initial state X naught. And I'm going to drop this later, but these are all going to be vectors. Likewise, we have terminal cost phi F, which is based on the final time and then the final states. And then lastly, we have some path cost that's integrated from initial time to final time, which is L, and that's dependent on T, X, and U, and dt. So that looks like what we had before, but now we have initial cost and final cost, which I don't remember if we had those before. And then this is subject to some dynamics, which is x dot is equal to f of t, x, and u. And then we have initial boundary conditions, psi naught, which is based on initial time, initial state. And like I said, that's an initial boundary condition. And then we have the terminal boundary condition, likewise, is based on the final time and final state, and then that's equal to 0. Just as a quick note, the reason why your terminal costs and also initial and terminal costs and initial and terminal constraints are not based on the control is at that point you could set basically the control to anything. So maybe you might think of some edge case where the control will make sense to be in there, but in virtually all practical cases, since you can set the control to whatever you want, any admissible control, you could re-express those constraints in terms of time and state. So yeah, the way we're going to go about this is the joined method. so the full adjoin method. So like we adjoined the dynamics to the path cost last time, we're also going to join the initial and terminal constraints to the initial and terminal costs. So we have some new cost functional J prime, and that's equal to the initial cost plus, and then Lagrange multipliers in this case are going to be new knots, and that's adjoined with E naught and X naught. Okay, and then likewise we do the same for on the terminal constraint. So we have the terminal cost, TF, and here I'm dropping the bars. Just assume everything's a vector, unless not time, but like, yeah, I think everyone knows what's a vector and what's not a vector. So we adjoin it with more Lagrange multipliers, new F. It's the same deal, but on the terminal boundary. And then lastly, we have what we did last time. So we have some integral from T naught to TF. The path cost with the dynamics adjoined. And as we continue with this, it's helpful to think, okay, this first term here, that's everything that's on the initial boundary. The second term is everything that's on the final boundary. And this is everything that happens in the middle. When you start dealing with path constraints, the same kind of thought happens. And if you could even think now, if you want to join equality path constraints like we did last week, you would do it to the path part. And that's kind of a helpful way to, like where the constraint applies, that's where it gets adjoined. Okay. Now I'm going to combine terms for simplicity. So here's a capital phi. I might forget the upper and lower bars on that. But this is basically the adjoined path cost. So we have a lowercase phi, and new naught. And likewise for the terminal, cost and constraints. And like we had last time, we also have the Hamiltonian. So that's has arguments t, x, and u. So the path cost and plus the co-states which adjoin the dynamics. But we leave out the x dot as before. So then, kind of simplified, drop the arguments here. We have big phi naught plus big phi f plus on the integral from t naught to tf of the Hamiltonian minus the co-states times x dot. Okay. So this is an unassigned, so it's not supposed to be an h, it's supposed to be an n. So note, now that T naught and TF are free, we need to account for the changes in time as well. So the variations that we dealt with last time only dealt with changes kind of vertically in the case, so with a fixed time. So variations change the variable while holding time fixed. And if you remember, we used that kind of like scaling to show that. So we scaled the function up and down, but we didn't slide it. On the other hand, the differential change consists of the variation and the time varying component. So this is actually easier to draw out, well, write an equation and then kind of draw out. So we have some differential, which is, in this case, we're going to say dx is equal to the variation in x plus x dot in the diff dt. So this is the variation from before, right? And then this is what changes based on time. So the change of time. Okay, so I'll draw this out. So this is going to be, this happens also on the initial boundary, but I'm just going to deal with the terminal. So we have some function. Actually, this is the original one, and then this is a new one. So let me drop this down. So let's first mark. I use a different color. Right here, like we had last time, is the variation in x. Oh, I'm sorry, I didn't label my axis. So this is going to be t, and this is going to be x. So that vertical distance is the variation in x. But what we care about is this here. So then we also have to account for, there's some change in t. So this is dt here, right? So we have this kind of, it goes this direction, and then there's a little, so if you like kind of propagate this forward, and these are infinitesimally small, so you have a slope here. So this is x dot, which is the slope, dt. So this entire thing here is what we're after. Does that make sense, everyone? I'll take silence as a yes. Okay.
Yeah, it makes sense.
Thank you, Eli. So, and before we proceed to the rest of the derivation, I'm going to revisit Leibniz's rule, so we have it. And I think I'm writing this differently than I did last time, but it's the same thing. So we have some differential and integral, some generic function f of tx dt, and in our case, that's equivalent to, you can think of it as like, let me write it this way actually. So you have the variation in this integral dt plus, and then you have the So that's this variation term here, and then we need the second one. So we have some f dot dt, and then that's integrated over dt. So what that comes down to is we have the variation, so this term stays unchanged, but we more or less can pass that through like we did last time, plus, and this is what I'm getting at, which is different than last time, we have f dt, and then that's integrated from t, like evaluated from t naught to tf. Okay, so returning to j prime, let's take differential of j prime, and of course, let me write it. I don't have it right in my notes, but we're going to set that to equal 0. So let's just, so I have it with us. Let me just copy this. Probably would have been faster just to write it, but whatever. Using the technology. Okay. So we got 0 is equal to dj prime. And now we're going to take the differential for the first time. So what that looks like is the partial of phi naught partial t dt plus partial phi naught partial over x dx. So that is and that's evaluated at initial time. Likewise, we do the same thing for the terminal time. And this is why I included both, just to make it so we don't have to spend more time, because you just kind of copy. It's a little longer, but you do the same thing regardless if it's on the initial boundary or final boundary. And then this is where Leibniz rule comes in. So, well, basically, when we take the differential of this term, we take what's inside and then we evaluate it here times the dt. So that's what this is going to be. And then we have everything that's in the integral. And then this looks exactly the same as what we did last week. Okay, like we did last week, we can clean some things up. So the first one is that this here, this is equal to, because the partial of the Hamiltonian with respect to the costates is f. So then this term, what's here, simplifies to f minus x dot, and then the variation of costate lambda. And because f is equal to x dot, this is equal to 0. So this whole thing is 0. Okay. And then, as a side note, this is also this term here. Let me pull it out here. this is equal to original path cost. Okay, so now we do the other step, the other kind of trick that we did last time as well. We have an integration by parts. And so everyone, well, let me just pull out the part that we use. So remember, we integrate this last term here. We want to get rid of this variation in x dot because we don't want to deal with that. So this is equal to negative lambda transpose the variation in x to evaluate at both points. And we have the integral from t naught to tf of lambda dot transpose and the variation in x. So applying that to our expression for the differential in J, you get, this is just a lot to write, but it's not that difficult when you know the process. So initial terms, and of course these are capital fees. Okay, so the things that are different here are so if you look up here, I simplified that path cost, simplified it here, and then also did the integration by parts. And then we're going to collect some terms again. And then let's also remember the kind of variation, but I moved it around. So, see, this caught me off guard when I looked at my notes in the past, so let me write it out explicitly. So if you remember, we have the differential in x is the variation in x minus x dot dt. So then we arranged to solve for the variation. So we get the variation is equal to, plus. This is a plus, and then when we rearrange it, we get dx minus. So we're going to use that and plug it in with the variation in x appears. So we get the partial, the initial constraint with respect to t, but then now we add this path cost term. And then that's all multiplied by dt. And then from now, the partial with respect to x is still multiplied by dx. This, because, yeah, you know that this is LDT at TF minus LDT at T naught. So that's where this minus sign comes from. We do the same thing, but at the final point, but this time it's a plus. And then I'm applying that note within this term here, this one. So we get lambda transpose dx minus x dot dt. And then we get the same integral as before. Did I? Oh no. I'm sorry, we don't get exactly the same integrals before. We combine terms. So both of these variation terms, so this plus this up here, we combine them together. Okay, now we're going to continue on combining things together. So this time in the initial cost, well, sorry, I got ahead of myself. So we have what was initially here, and then we're going to take off the part that is multiplied by dt is going to go into here. So this is minus, minus is a plus, but it's the t naught component, so it's a minus. That, and then that's all by dt. And then we have the same here as we had before. But now we're going to add this component here. It's minus, minus is a plus. And then for the terminal, everything looks the same except the signs are switched. Like I said, the signs are switched. And lastly, we have what's inside our integral, which now I think it's the same as above. We're almost there. And the last thing to know is that if we look here, this is the Hamiltonian, right? Because we have, well, it's negative Hamiltonian, because we have minus the path cost plus, and x dot is equal to f. And likewise, this is the Hamiltonian here, because we have L plus lambda transpose times x dot, which is the same as lambda transpose times f. So we get a kind of final thing. So we did the initial, and this is the terminal. I've actually thought in the past of changing the sign for the costates because I don't like the fact that it changes. You have a minus here and a plus, but I would be the only one I know in the entire world that does that, so I'm going to stick with everyone else, even though it bothers me a bit. Okay, and then now we have the fun game of setting every term to 0. So we set this to 0, 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 and that to 0. And we get unnecessary conditions. So from this first one right here, we get lambda dot transpose is equal to the partial derivative of the Hamiltonian with respect to x. And then, like before, our control law is setting the partial of the Hamiltonian with respect to u to 0. And then we get, so that is the past portion. Now let's do the initial portion, but the time, the kind of time, the dt ones, so the ones that cancel the difference in time. So we have equal to 0, the partial of this combined adjoined initial cost minus the Hamiltonian at time 0, which, if we unpack that adjoined, just so we see everything, we get the initial cost, the partial of that with respect to t, plus nu not transpose times the partial of the initial constraint, boundary condition, okay, with respect to t, minus the Hamiltonian evaluated at the beginning. Nearly the same exact thing happens at the terminal constraint, but signs are switched. Alright, this is still plus, but this is also plus. Now the last thing to add is the ones that cancel out the variation of states at the beginning and at the end. So we have the partial of the adjoined terminal cost plus the co-state, the initial co-state values. And we expand that out as before. Oh, this is not t, it's x. And this kind of like points to something interesting as I'm writing out the same thing for the terminal. Oh, so this is initial here too. So this is all initial. As I'm writing out the same kind of thing for the terminal, this is a note. Mike Spiapani noted this for his PhD work. It was important to him for some reason, for the advanced math he was doing. That the Hamiltonian, in a way, if you make time a state, which in some cases you want to act like it, the Hamiltonian ends up being like its co-states. And you can kind of see how that's the case when you adjoin everything. I believe I said that correctly. Maybe if he watches this, he would correct me, but it's not super important. Okay, so these are all the derived necessary conditions, and then that's in addition to what we have, that x dot is equal to f, psi naught is equal to 0, and psi f is equal to 0. So we just to prove to you that we have enough conditions, we originally started with t naught was unknown, Pf was unknown, x was unknown, u was unknown, and then we added, let me just say it, but write it normally. So then we added, for x, we added a costate's lambda, and for the initial boundary conditions, we added unknowns, nu naught and nu f. So in this case, here we have one unknown plus one unknown plus n unknowns plus m unknowns plus n unknowns plus, I'm going to say we have p initial constraints and q final constraints. So this is plus p plus q. So then we have, that's 2 plus 2n plus m plus p plus q unknowns. So what do we have? So we have p and q equations here and here. Here we have n differential equations, which then we need n algebraic equations for, which are gotten here. Right, so this is n, I'm running out of space, but these are n algebraic equations. And then here are n differential equations as well. But luckily here, well not luckily, but planned, here are n algebraic equations. And then here are m algebraic equations. And then here is one algebraic equation. And then here's another algebraic equation. So we have everything that we need. Okay, and then before I move to stumbling through examples, I want to point out something else that is interesting. So as of now, the Hamiltonian, which you remember is H is equal to L plus lambda transposed F, right? This is actually, this Hamiltonian, as I'll show, is constant in most cases, and you can actually show really easily when it's constant. The condition for constant Hamiltonian. So if we just take the time derivative, so d dt of h, and this is just doing the chain rule, I guess. So we have the partial of the Hamiltonian with respect to time, and then the Hamiltonian with respect to taking the derivative with respect to the states, with respect to the costates, and with respect to the control. And if we remember, optimal solution, we have dH is equal to d partial of the Hamiltonian with respect to the control is 0. We have the partial with respect to the costates is equal to the dynamics f, and then we have the time derivative of the costates is equal to the negative partial derivative of the Hamiltonian with respect to x. So we just plug those back in. We get, so this partial with respect to time stays, but instead we get, so here we get a negative lambda. Let me make sure I copy this. I'm sorry. This stays the same. Yeah, you could do it multiple ways, but this is going to stay the same. And I'm just going to say it's f, and then this one here is equal to, we get a minus so it ends up being the same. I kind of double transpose, so then this is this transpose, but it's an inner product, so you could transpose the whole thing and get the same function out. So this is equal to 0, obviously this is equal to 0, and then we get the time derivative of the Hamiltonian is equal to the partial derivative of the Hamiltonian with respect to time. Therefore, the Hamiltonian's constant if it's not an explicit function of time. And that's pretty common, because unless you have time explicitly in the dynamics, which often isn't the case, or you have time explicitly in the path cost, which is often not the case, then you have a constant Hamiltonian, and then you can track its staying constant as a condition. And then also, if you check here, if you look at this condition here, the Hamiltonians almost always, so these can be the same in most cases, and like if you don't have an initial cost, and that your initial time, well, yeah, a lot of times it's 0. That's basically what I'm trying to say, but that doesn't matter. It's more important that it's constant most of the time. So, okay, with that, if is there any questions before I go through trying to solve some examples?
Sean, can I add something?
Yes, go ahead.
Yeah, so the very last line that Sean has written here, the Hamiltonian is constant if it is not an explicit function of time. So in many of the papers that I have worked on and other lab mates, we actually used to check this condition because this is actually, it tells if the result that you got is really optimal or not. So one of the ways to check is to check the Hamiltonian plot. So this is one neat way of using indirect methods to see if your solution is really optimal or not really optimal, because mostly Hamiltonian is a constant value.
And correct me if I'm wrong, but that's also if you remember last lecture, I talked about I mentioned the covector mapping principle that relates costates to the KKT multipliers.
Mm-hmm.
I've seen in papers that use direct methods, they will convert the KKT multipliers to the costates, derive the Hamiltonian, and to show that the direct method is optimal, they will refer to the Hamiltonian being constant as well.
Exactly. I think they work on the similar principle.
Okay. So I apologize that these examples might be I might have to try to figure them out with you guys. I honestly just ran out of time when I was trying to pre-write them out. So bear with me. And we might just work through one, and then I might then put a more thorough examples up for practice up on the GitHub. So let's work through this. Like the Chrome, this is probably the second most common problem. It's actually a little simpler. It's Zomilo's, I'm going to put boat here, boat problem. And you see a lot of variations of this, and I've made variations of it to like try to prove it's kind of like if you develop a new method, like a new way to bound things, you can modify this problem pretty easily and then have it as like a proof of concept. So in the simple form, we want to minimize time for a boat to cross a river with constant current W. And then also, so let me draw this out. Let's use some colors too. So we have one side, the other side. Say a boat starts here, and we want it, we actually care at this point. So say for illustration, and because I have some time to spare, I'm going to draw a little dock here. Because, yeah, you can picture. So you want to hit this part of the river, and I'm going to label this. This is going to be X, and this is going to be Y here. And then we have some currents. You see variations of this problem where this current is different. Sometimes you'll see a sign. Sometimes it's changing with time. But right now it's just going to be a constant current going down this river. That'll be W. And then I'm going to draw a boat somewhere in the middle here. And it'll have a constant velocity V, which is measured off the x-axis by some theta. And in this case, so let me define. So here we have x is equal to xy. I always get ahead of myself. This one has two states, x and y. And then u is equal to theta. So f is equal to the velocity cosine theta, and then a y is sine theta plus w. Alright, hopefully that's pretty clear where I got that from. Excuse me. Okay. So we minimize J. We're minimizing time, so it's equal to TF. But I'm going to convert that to the past cost, like we did with the Chrome problem. Actually, I'm just going to keep this 0. So initial time is fixed. Okay. So, and then constraints are, let me just move them up here so I save space. So we start out with x and y being 0, and then we have final time, we have x minus 1 is equal to 0 for this problem, I'm going to say that this whole distance is 1. Well, actually, I'm going to genericize it. I'm going to say this is equal to x, final x. And then we want to, this is on the same, these dots are on the same line. So we have y is equal to 0 as well. Okay? So Hamiltonian is equal to 1 plus, so I'm going to say lambda x, and that's the cosine theta, plus lambda y, the sine theta plus w. And then, so lambda dot is equal to the partial with respect to x transpose. And notice in the Hamiltonian, neither state appears. So this is 0 and 0. Therefore, lambda x and lambda y are some constants. I'm going to say C1 and C2. And then control. I'm sorry, I should write it. So now we deal with a control law. So the other condition is we have partial with respect to u is equal to 0. So then this is equal to lambda x v, so negative sine of theta, plus, we do the same thing, but we get lambda y v cosine theta, and that's equal to 0. And then we want to solve for theta, so that, right, we move this to that side, and then divide, ends up being tangent theta is equal to let me make sure I have this right. Lambda y v over lambda x v, which then is just equal to lambda y over lambda x, which then is actually equal to a third constant. Because all these are constants, right? So we get a third constant. So, but actually, so theta is equal to the arctangent of lambda y and lambda x. Watch out. Say it's C3. Okay, now we can turn to the constraints. And then this is where my notes don't actually match because I have this problem solved for the unenjoined method. So bear with me. Okay. Actually, we're going to go back and do this a little different. Not differently than my notes, but if you remember that x dot is equal to the cosine theta, therefore x, if we integrate, right, we get x is equal to the cosine theta times some time plus an integration constant. And because x at t equals to 0, is equal to 0. Therefore, so when this is 0, this is 0. C4 is equal to 0. So then we get x is equal to Vt cosine theta. And then x at t is equal to 1 is equal to 1. Therefore, we have, well, V cosine theta times TF. Is equal to 1. We can do the same thing for y as well.
Didn't we set that xf to just a generic xf?
I did, and then I changed my notes. So thank you. There we go. Thanks. Yeah, this is, once again, I'm sorry I ran out of time, and I had to think about this more than I should have to. But we did the same thing for y, though. Y dot is equal to V sine of theta plus the W. So then we integrate at the equal sign. Five. So y at 0 is equal to 0. So then that it means C5 is equal to 0. Y at TF, and this is TF up here, is equal to 0. Therefore, V sine of theta plus W TF is equal to 0. TF is non-zero, so then we get sine of theta is equal to negative W over V. And then, yeah, so we get our optimal solution, which we proved is constant. And I guess this might have not been the best example because we don't actually have to use the constraints, the joint constraints and everything. And that's because the reason why it doesn't even show up is because we specify the states both at the beginning and the end. So this really takes advantage of the free time. But and maybe I'll go through that after I write this out. But because the states are specified at the beginning and the end, the extra joint variables aren't needed because so I'll talk about that more after that. But then optimal control is that which we solve for, which is explicit for all time. And then we could back solve. So if we basically plug this into a solution for TF, which I think I got up here. Let me just, what did I put in? Maybe I didn't write it out. Oh, it's this X one, right? So we have XF is equal to V cosine of sine negative WV, that's is equal to TF. We remember that cosine theta 1 minus sine, good. Theta which is 1 that's a W over V squared, which is equal to v squared minus w squared over v, and then we plug into up here, and then we get TF is equal to XF over v squared minus w squared. Okay, so that's the Zamilo's problem. It's probably one of the simplest optimal control problems, but you end up just, really what happens is that the way this works is you head into the currents, you face your boat into the currents such that your motion's only along this line. So you kind of go a straight path, but your boat will kind of face this way. Okay, and then instead of fumbling through another example, I'm just going to point out a few things and probably let you out a little early. And then look out when I get them up there, which I'm behind. But when I get practice examples out, there'll be more examples. And of course, if anyone has a question over any practice examples or anything I put out, just contact me. Okay, so if you remember with our unenjoined method for so this enjoined method, we get expressions that are like always true. When, if you remember the unenjoined method, we had the conditionals. So the conditionals were if x at a boundary is constrained, then lambda is unconstrained. And if x was unconstrained, then lambda was constrained. That still exists here. It's just embedded with the adjoining. So let me pull out this expression here. Let me copy it and actually put it down lower. So this is a terminal. Let me just say terminal turn. Say the same thing exists for all the other ones. So if we picture here, and I miswrote that this is an x here. So let me go up if I could see. Sorry. Yeah, this is x. Yeah, so if we look at this here, you could picture if xi is constrained, then that means it shows up in this constraint vector. So, and I guess it doesn't have to be that particular element, but let me actually list it as that. That's correct nomenclature. So the partial of this, I guess it ends up being the same, but basically, if this is constrained, this partial is not equal to 0. So if this is, so lambda f comma I is equal to 0. No, it's, hold on, let me think for a second. Basically, no, it doesn't have to be equal to 0, but, so, what's the right, how did I say this? Let me think for 1 second. If this is not 0, then this together has to be oh yeah, so this isn't 0, but that means this is the way to say it. New, the ith elements of new can change to make equation 0. So that's the proper way to say it. So if this term is not 0, I can set that element of new to be anything to balance out these other two terms. So new is constrained, but these other two, which includes this final co-state, is free. And the Fi is free. Likewise, if Xi is not constrained, then this is equal to 0. So new is unconstrained. Well, let me just say free. I'm sorry. Let's say this is free. And lambda Fi is constrained. So if we go up here, and this is 0, this new could be anything, and it's not set. Like you could set new to be anything, and then this term is still 0. So this lambda, this terminal lambda is set still based off of whatever the cost function, the terminal cost function is. So it still has this dynamic. It's just embedded using these Lagrange multipliers, that if x is constrained, the co-state isn't, and vice versa. I hope that made sense. I did that on the fly. I forgot to write it in the notes. So, any questions? Anything anyone would want me to talk about? We have 10 minutes free.
I think I get it. Thank you, Sean.
You're welcome. And if that's the case, then I'll let you guys off early. So thank you very much for listening. And I hope to get stuff updated as soon as possible.
Thank you. See you soon.